Hey everyone, this video is intended to help show you the math you do when solving a titration calculation, as well as to explain a little bit more about how the experiments themselves work. So with a titration experiment, you either typically have a solution of an unknown acid or base. And in our particular case, the unknown is the concentration of sulfuric acid. That's the H2SO4. And the base is sodium hydroxide, and that is a known concentration. So if you look down to our knowns list, the molarity of the NaOH is 0.250 molar. And that's the standard solution. The standard solution is the one for which we know the concentration. And the NaOH is in the burette. And so you load the burette up with pretty much all the way to the top with NaOH solution. And you don't need to load it up to the 0 mark on top. You just need to write down the starting volume. So that volume, if I do a sort of close-up of what the burette might look like, if this is the 0 milliliter mark, and the way the burettes are typically oriented is that the 0 mark is on top, so that if you were to load it exactly at the 0 mark, that means the bottom of the meniscus of our sodium hydroxide would reach up to the 0. Now you really could just load it anywhere you want to up near the top, as long as you write down that amount, because it's not so much, right, the starting amount that matters, but ultimately how much you put in to our acid solution below. And so our acid solution is H2SO4, and that's where we put below. Now, the amount that this experiment has in it is 26.60 milliliters of acid, and it's a little bit of a wonky number, but it doesn't really matter how much of it is you put in there. Typically, you measure out an exact amount with a volumetric pipette or a graduated cylinder, something along the lines of 25.0, a nice even number, but in this particular case, that's how much was put in below, 26.60 milliliters of our acid. And with this particular experiment, we're determining the molarity of that acid. So in order to do this, you need to write or have in front of you the balanced chemical equation. And if you look to the top, we have H2SO4, 1 mole of that reacting with 2 moles of sodium hydroxide. And as you recall from our acid-base neutralization reaction, the reason why is because each OH combines with 1 hydrogen from the acid to make 1 water. And in our particular case, because sulfuric acid is diprotic, it has 2 protons, we need 2 moles of base to fully neutralize it. And what we produce is sodium sulfate and water. Now, sodium sulfate is also aqueous, and water is our solvent, which is why we write that as liquid, because it would not make sense to write water dissolved in water. So there's no solid form. The sodium sulfate that is formed remains in the solution below. So we turn our stopcock and we start to drip the base below, and what our data tells us is that, oh, I forgot, we also add our phenolphthalein to this solution. And the phenolphthalein is our color indicator. And the phenolphthalein is clear in acidic or neutral solution, and it turns pink in basic solution. So we add that first to our acid before we start the titration. We drip in and we find that we have added 32.20 mils total of base. Now that could, if you started at the 0 mark, that means it ends at 32.2 mils. If you didn't start at the 0 mark, if you started somewhere here, like at 0.5, right, it's the final minus the initial volumes added. And because we started at 0 here, the final amount is simply reading the burette to 32.20. But if we started at, let's say, 0.5, we would have to subtract the final volume minus the 0.5 where we started, because what this really means is volume of NaOH added. So now that we've got our data, right, what happened was the solution turned pink when we added 32.20 mils of base. Now it only turned slight pink, which means that we're right at that point, right? Slightly past the point, one drop over the point where all of the acid has reacted away. And to sort of give you a little bit more of a visual representation, right? Just to make sure you're understanding, as what's basically going on, right, is you have your H2SO4 molecules in here. And each time, you drop your NaOH in, right? And NaOH, right? 2 moles of the NaOH react with 1 mole of the acid to produce water and the sodium sulfate. But what's happening, right, with that last drop is that all of your H2SO4 has now been reacted away, and that last drop of acid of base that falls in has no neutralization reaction, right? Has no acid to neutralize it. And so it essentially now hangs out as additional NaOH in your solution. And because of that, the NaOH now makes that solution slightly basic. There's no more acid to neutralize it. So the solution is slightly basic, therefore turning the phenolphthalein indicator pink. So now that we have our data, we're going to do the math involved in this particular reaction. Now, what I like to do is I always start with my base. And with my base, I look at the molarity. Now, the molarity is 0.250 molar. So I don't write it, though, as 0.250 molar when I'm doing these types of calculations. When I'm trying to figure out how many moles I added, I break down the molarity into moles per liter. And that's moles of NaOH in 1 liter. So the reason I do this is because I want to know what to do mathematically. And if I left it as molarity, because molarity is a ratio, it's less obvious to know what to do. So when I see it this way, I know that molarity is moles per liter. So 0.250 molar means 0.250 moles of NaOH if I have a full liter. But I don't actually add a full liter. What I've added is I've added 32.20 milliliters, but that turns out to be 0.0320 liters of NaOH. That's 32.20 milliliters. I simply divided by 1,000. What this shows me is that my liters cancel. Because when you multiply by a whole number in this sense, right, it's like multiplying by liters over 1. And you can write any whole number as a fraction over 1. And so that shows you that by multiplying the volume, I now can isolate the number of moles of NaOH added. If I stopped there, I'd be answering the question, how many moles of sodium hydroxide were added when I multiply those two out? However, what I really want to answer is the molarity of the acid. So I need to relate the moles of base to how many moles of acid they must have reacted with. And in order to do that, I go back to my balanced equation. Because it is not 1-to-1, and in fact 2-to-1 of base to acid, it's not the same number of moles. So if I added however many moles of base, this 2 in front of the NaOH tells me that, in fact, for every 2 moles of NaOH, I must have reacted away 1 mole of H2SO4 because it takes 2 moles of base to react away the 1 mole of acid. The reason I put base on the bottom was so that the moles of NaOH would cancel diagonally. Now that I know the moles of acid that must have been below in my Erlenmeyer flask, I have one more step. Because molarity is a concentration, it's moles per liter, I'm going to do one more step. Now that step is dividing by the volume of acid that I added. The same as, well, multiplying by 1 over is the same as dividing. How much acid did I add to that flask? And the amount of acid, according to my data, was 26.20 mils. So I'm going to convert that to liters, dividing by 1,000, 0.02660. So now, moles of acid divided by liters of acid. All of my other units have canceled. Moles per liter is molarity, and that's the key to understanding this. So when I do my math, I take 0.250 times 0.03220 divided by 2 divided by 0.022 or 2660. When I do this math, I end up with 0.151 molar H2SO4 because the moles per liter is better represented as, in the answer, as molar because I was asked to determine the concentration of the acid below. So in summary, our steps are: number 1, either read or write the balanced chemical equation for the titration that is happening. 2, understand which of our 2 solutions is the standard and which is the unknown concentration. 3, look at the data. Notice what it's telling you. You need the molarity of your standard, and you also need to know the volume of the standard that was added. In our case, it was the sodium hydroxide. Also note whether you are told the volume of NaOH added or whether you are given the starting versus the ending volumes added. Because if you are given the starting and the ending, right? If, let's say, your ending was 28.75 milliliters and your starting was 0.5 milliliters of your standard, then you would actually have to subtract the 0.5 from the 28.75 in order to get the total mils added. Step 3, make a note of how much of your unknown has been put in the Erlenmeyer flask below. You always start with your standard solution, breaking down its molarity into moles per liter as we did in step 1. Step 2, you multiply by the volume you added so that you are determining the moles of standard. Step 3, look again at the balanced chemical equation to see if it is a 1-to-1 ratio, a 1-to-2, 2-to-1, who knows. Step 3, divide by your volume that you originally took of the acid or the base, depending on which one is unknown. Then you simply complete the math in your dimensional analysis, writing your final answer, typically not as moles per liter, but as molarity. So these are the steps that you'll follow each and every time when calculating the molarity of an unknown acid or base in a titration experiment.